Everybody in this business seems to have a long history. That's a good thing, I think. It's a sign of a good ecosystem where so many of the players have seen so many different waves of innovation in the field and are still in the field. It's not exactly a common thing, I think. Gidel was founded back in 1993 and started building programming tools in 97. And we were talking earlier, and you had explained how that time was kind of a watershed moment for FPGAs. And I wanted you to explain to us what was going on back then when you first started doing development tools and decided to do tools. And how has that led us to this place where we're at today? And then we can talk about what do we need to do, just very generally, what needs to be done yet, from your point of view, as someone who is engaged in helping people figure out how to use these devices as opposed to just building them and creating the tools that helps them program them better. So go ahead, tell me what's going on then.
So first of all, thanks. Founding Gidel at 93, we already started with FPGA algorithms and with overlays and all the new things people are talking. We started at 93.
Right, so this sounds like old technology to you in certain ways.
So I wouldn't say old, I would say known.
Known, established. Forget.
And more we've done, we had more experience of what customers are looking for. And at those days, we had to build something like boards with 30 FPGAs.
Right.
And I used several boards of them just to complete one task. And the overlays used to enable different requirements for customers to replace according to the needs of that time. At that time, for each application, for each algorithm, you had to build a dedicated board.
Right.
With dedicated memories associated to the algorithm. So it was very, very titled. And therefore, you have built them only on a very, very specific things where it was either you do it or you gone out of business.
Right.
In 97, with Altera having the dual port RAM inside the FPGA, compiled with our memory controller that enabled to take a regular DRAM and split it into several logical memory with streaming data in and out according to the application needs. We found out that it's a time possibility to make a generic platform or boards that will be able to suit different application and different algorithms.
And you could do stream processing as we think about it back then.
Yes,
You've had that capability. And which industries grabbed that first? Which ones took that technology first and started deploying it?
So the first one to grab it are the industries that use FPGAs before the common boards.
Sure.
And that was imaging and vision application to start with. And interesting-wise, some things that with the supercomputing, when I'm looking at it, there's two major type of applications. One is like the vision application, where you have algorithm A delivering the data to algorithm B to C to D, and you have to put a lot of investment to do every type and everything separately and combine them all together. The second one is more typically in the supercomputing, and that you build a processing element and then multiply that a lot according to the resources you have.
Gotcha.
And in that case, you need to put much less effort in the overall development with the FPGA. So we've seen in both cases, depending on what you try to achieve.
Gotcha. Back in 2009, going to another thing that I thought was fascinating, and I've joked with Ivo in the past, like, when am I going to see my supercomputer made out of FPGAs? And you obviously have done it. So back then, there was a machine at the University of Florida that I think had 192 FPGAs and a head node with some Xeons in it. And they were this was a very, very fast machine for genomics, built on FPGAs that you helped integrate and build. From my math, looking at it, I think that the numbers at the time were that system, 24 nodes, was able to run particular algorithms in genomics 150,000 times faster than a single Opteron core. And if I sort of convert that back to how big of a rack of, pick a number, 48 Xeon or Opteron servers, it's like 500 to 600 times as fast as an equivalent CPU cluster at doing that work. That's an amazing thing. So
yep.
What did that teach us? That's the first thing. And then what happened? Because we didn't have computers that have acceleration with FPGAs, supercomputers. We have GPUs. And I'm wondering, is this going to come back around again? Is it time? I think we want a rematch, because we have some really, really impressive FPGAs now, and interconnects and memories and et cetera.
So first of all, yes, and that was we had then boards with 4 FPGAs, and so the initial one was with the number that you said. Then there was the second generation of the FPGAs, and it grew to close to 400, and then it grew to close to 500 FPGAs, and still in a very simple area. And with the tools, it enabled to work with different generations and still combine together, so you don't need to throw away your initial investment. The other thing is there was also, for the molecular dynamics and other things, ability to do a direct 3D torus between the different FPGAs, at least 32 or 64 FPGAs.
We've heard that from Microsoft. They were doing a similar thing,
yeah, so
much later.
Yeah, so that was actually the Novogy people used to say that that's the largest FPGA cluster in the world, in the known world. And when Microsoft came with the Bing, then they changed. Okay, that's the largest research known.
Right.
But it is definitely a giant, and definitely ability to see that there's a lot can be done. You asked an interesting question about the bioinformatics. So no doubt with bioinformatics is one example, and many others, that the FPGA would get much better results. However, the market and people way of thinking, they expect to get the same results. So even if you can make with the FPGA a better results, and BLAST algorithm, for example, I mean BLAST of biogenomics and not mathematicals.
Understood. There's a T, I assume. Yes.
Sorry. So it's not accurate. And you can, even if you get a better accuracy, people would use, no, give us the same results.
Right.
And when you're doing optimization in FPGA, we've done many times taking a code from C and making the optimization in FPGA. So number one of the tasks, get rid of software optimization. Because the way you optimize in FPGA is not the way you optimize in C. And within the genomics, there's a lot of work done in optimizing code in software, in CPUs. And therefore, it makes it hard to go and make the changes in the FPGA. Once the public would be aware more about, we can get much better with the FPGA. We can do that with FPGA optimization. Then I think you would see a jump in bioinformatics using FPGA, because no doubt CPUs and GPUs just cannot compete with FPGAs in that market.
Sure.
But the industry needs to understand that and to accept it.
And there's a mind shift that has to happen too. You have to, if you really want to fully utilize the FPGA in the way it's intended, the idea is that you can take the data types and the bit lengths of things and match them perfectly to the workload.
Yeah.
And you were doing that on this particular machine, I understand.
Absolutely.
And that was, again, before there was a TPU and bfloat 16 and all this other stuff going on. And it proves the point that we now have learned because of machine learning and deep learning that, the adage from Google was more data beats a better algorithm every time. This is similar to that in that, you can sacrifice some of the accuracy in the data and still get a better, or more importantly with an FPGA, a faster result.
So the bioinformatic example that you gave, the nature data element is 2-3 bits per data element. With vision applications, sometimes it's just 1 bit.
Right.
So in these, it's very obvious that the FPGA can accelerate.
Sure.
And the interesting things is applications such as the deep learning, when it started with a floating point and you got a certain results. And if you're looking at fluid dynamics and other things, people are saying, okay, we need floating point, maybe double precision, or maybe single precision, but no way someone will accept less resolution. With the deep learning demand, Google came up with and said, well, 8-bit would be sufficient to start with, and maybe even less. At the computer level, less than 8-bit or 8-bit was the same.
Right.
But the fact they said, well, instead of floating point, you go to 8-bit, and then you get just 1% less in the accuracy of the deep learning, enables people to say, well, now we can do much more. We can have more layers, or something else more sophisticated.
And push that many multiples of data through the system.
And get much better accuracy at the end. Or in fluid dynamics, if you'll be able to have less accuracy of a single computation, but have more thinner elements, maybe your total results would be much better. And Google had enough energy for people to open their ears and understand that in different markets also, maybe using less accuracy of a single element, but running faster and getting better results, or trying several random numbers to start with, you'll be able to get a better result. And that, I think, is crucial for understanding that there's a place for all kind of application to use the FPGA that uses exactly, and you pay exactly for what you need, and you don't need to pay for any more bits.
So having learned all these lessons, and we're at this point where people are used to thinking about mixed precision, they're used to thinking about application offload, not overload. What is the obstacle now? What are we looking at today? What's the real problem or list of problems that you see? Because you're helping people. You're not just developing tools. You're helping them figure out how to do this stuff.
So I'm looking from two different aspects. One aspect is set of mind of people. Making a data flow within hardware or FPGA is not as data flow in CPU. And making algorithms is not the same algorithm to be optimized. And if your set of mind is, okay, this is the algorithm that would work well in CPU, and I'll develop the algorithm, and then I'll give someone else to translate that into the FPGA, you would not get the same results as if you think from the beginning, this is my problem, what would be the best algorithm to fit that within the FPGA? Okay, so this is a set of mind. The other set of mind is, if the FPGA can give a better results, why does it need to give the same result as the
it's a mind
software? Yeah. So this is one thing, is a mind shift, mind thought. The other thing is, I think we reached today to a position where people acknowledge that in all kind of fields, especially in the data center, with the FPGAs, you're going to get better results. And The same that happened with the algo trading. I remember in '97, people told me, no way FPGAs would be in algo trading.
Right.
Now I think, no way it would not be there.
Right.
And I think the same would be with data center.
These things often do a binary flip. I mean, we went from federated clusters of big NUMA servers for supercomputers, and then Beowulf clusters came out, and Linux came out, and everyone said, no way, we're not going to do that. I think it was 3 years, and a vast majority of the new supercomputers look more like that than they did like the past. So for reasons, they hit walls, and they have no choice. Yeah. Are we at that point? Are we at that point where people have no choice?
I think nobody talked about it, but I think the FPGAs is excellent for innovation. Mm-hmm. It has so much freedom inside and so much to do next with the FPGAs. Mm-hmm. So with all the respect to me and to the audience here, we know nothing compared to the world innovation capability. Mm-hmm. And I think it's excellent position for innovation. And in general, the fact that the large companies have accepted the FPGA, start moving with the FPGA, made everyone understand that it is serious, it's here, and let's give it a shot. And so I think the atmosphere is absolutely for the FPGA to grow. I believe that performance is crucial, because if one would put in 3 times more effort in development mm-hmm. and get 3 times better performance, they'll be able to beat all the others that would try to reduce the effort.
Right.
So over these years of 20 plus years of development tools, we looked always on 2 edges, the performance and the ease of use. Mm-hmm. And we kept the performance to the maximum and stretched the ease of use on one hand. On the other hand, from time to time, we took the ease of use to the maximum, enabled software engineers to run and stretch the performance as much as possible, and hopefully to switch in between right. as we can.
And grow both vectors.
Yeah,
I mean.
But when it comes to simple project or a small amount of project, a research project, going with a regular CPU, maybe it would cost more, maybe whatever, but it would be much faster to develop, mm-hmm. and that's the best way. When you go to deployment of huge investment,
right.
if you don't get the maximum performance, you're losing a lot of money.
Yes.
And I'm taking the financial market just as a wave to look of what's going to happen. Mm-hmm. And I was amazed to see a bank IT manager understanding everything about the FPGA, including where he can hire excellent people with lower salaries.
Right.
So totally understand of everything within that market and get the results. And that was, okay, latency is the critical, then it would never be with a tool that sacrifices latency. Mm-hmm. If total performance is the most critical, they would not reduce the effort if it depends so much on the results. So unlike the others, I believe that we need to see the flexibility and the ease of use, not sacrificing performance.
Right.
So, for example, within our tools, we were able to enable several programs accessing the same FPGA at the same time, working together, and that we reduced the development time because we took off-the-shelf products mm-hmm. and move it. To extreme, I'll give you an extreme case that happened to us. We took a frame grabber application using a certain board with a certain FPGA, and we had the customer, he said, well, we need it in another board, in another FPGA. Yes, we compiled, but it took us 2 hours to port the product mm-hmm. from one board to another board with another FPGAs just because the tools environment enabled us that.
Right.
We did a code review, making sure that it's only a single compilation. But that's really too extreme to understand that not necessarily it would
different
take...
vendors' boards or different
No,
boards?
it was our boards.
Oh, your boards, okay.
It was different generation of the boards, different FPGAs.
Okay. The gap was smaller than I might think it would be.
No, but I'll give you another example. Last year, we developed a product enabling image processing IPs to be done immediately, focus on what they want, with stimulus coming from the either API or a disk with a GUI and everything, going out to the frame grabber, storing, displaying, whatever. Okay, and you're focusing on your IP with a dedicated program. Well, since we started saying we want this, until we had a product, it took us less than a month.
Right.
And that product had 3 different boards, 3 different FPGA flavors. It's running from Stratix 3 to Stratix 10 and whatever. So this is an example where you can use tools and not sacrifice performance.
All right, I have to ask you one more quick question. I've talked a bit today about the idea that there should be a development environment that can span all these different kinds of compute. You're in that tool chain. You're not just hypothetically thinking about it. You're in it. What do you think about that idea? Is it possible for there to be some sort of development environment that can span all these different kinds of compute engines, not just multiple vendors' FPGAs? Is that desirable? Is it possible? Do you want it to never happen so that you can keep making money? I don't know.
Yes, we want to make money.
Yes, I figured.
But I think the most important thing is that the customer would succeed with their project. And they would use the best equipment to do that job. I do not believe that a single program would be better used with a single CPU or a FPGA or GPU. I think heterogeneous is most likely to be happened. And the system architecture is where to divide what would be where. And if you take, for example, an OpenCL code, it can be optimized for CPU, it can be optimized for GPU, it can be optimized for FPGA. They look totally different codes. So I don't see anyone writing a code. I'll reverse myself. With the tools today, I don't see anyone capable of writing a code that will run optimized on the variety of things.
I understand.
And since day one we started with the tool, the vision is to have tools that will be able to compile, optimize for the different ones. Like you take a C code, it compiled, optimized, whether it's 86 or ARM, with no problem. So I would eager to look to the time that, yes, we will be able to do that with a different
Will it take a long time? Short answer, because I'm running out of time, speaking of time.
I believe so.
All right, very good. Reuven, thank you so much.
Thank you.